In this chapter section, we will focus on organic compound called hydrocarbons, which contain only carbon and hydrogen in the molecules. We are going to look at the first type of hydrocarbon, which is alkanes. Alkanes are hydrocarbons compound with only single bonds. An example of alkane is propane gas, C3H8. The name of propane ending with "ane" indicate that this compound would be an alkane that contains only one single bond. Therefore, the structure of propane would be 3 carbons that connect to each other with single bond, and the terminal atom would connect it to hydrogen. Total of hydrogen would therefore be 8 hydrogen total. Alkanes are considered to be saturated hydrocarbon because it's not possible to add any more hydrogen into the structure. The process of adding hydrogen into organic compound is called hydrogenation. You probably heard this term before, hydrogenated oil. It means that oil has been added hydrogen into the organic compound molecule. And the word saturated you probably see often as well as we talk about saturated fat versus unsaturated fat, right? So pretty much the saturated fat would contain this single bond of an alkane, which means that you cannot add any more hydrogen into the molecule. The generic chemical formula of an alkane can be written as CnH2n plus 2. N refers to the number of carbon, and 2n plus 2 refer to the number of hydrogen within the chemical formula. For example, if n, or the number of carbon, equal to 3, the number of hydrogen would be 3 times 2 equal to 6 plus 2 equal to 8. Therefore, it's matching with the propane. And here are the list of the molecular formula of the alkane, some example of alkane. And as you see, all of these would fall into the generic chemical formula, right? So for example, if you have C10, the number of hydrogen would equal to 2n, which is 20 plus 2, which is equal to 22, for example. And this alkane, if you take a look at the structural isomer that we learned previously, you will see that they all have different number of structural isomer. Let's take a look at the first one, methane, right? So methane, you have CH4, which there would be only one available structure. Ethane would be only 2, right? So you have CH3 connect by each other, so that's also only one possible structure as well. Same as propane. Okay, so I'm going to erase this so that way we have enough space to draw the structure. So I'm going to draw these as the line angle structures to simplify it. So same thing for propane as well. There would be just one available structural one structure here. So that would be just one isomer. But when you have a butane, okay, so butane which have 4 carbon, another way that you connect these 4 carbon can be 3 and then have a branch right here. Therefore, total would be 2 structural isomer, right? And then if you have pentane, you can have 3 structural isomer, which we already talked about this earlier. So one would be the long chain with the 5 carbon. And another one is by moving 1 carbon and then connect it to in a different position, for example, like that. And the last one would be when you connect it all in 1 carbon, right? So that would be the 3 available structural isomer for pentane. And then you can keep going on, right? So you will see that the more you increase the number of carbon, the more you increase the structural isomer numbers for that particular compound. The next thing I would like to point out is that I would like to point out the number of carbon or the molecular weight of the alkanes, how that affects the melting point and boiling point, and also the physical state of the alkanes as well. As you see, as the number of carbon increase, you will see that the melting point and boiling point also increase as well. And according to this observation, we can conclude that the heavier the alkane, right, the higher the melting point and boiling point. And as you see as well, that's also affect the physical state, right? So the smaller carbon of an alkane would be in the gaseous state. The more heavier alkane would be in the liquid state. And the more you increase the number of carbon or the more you increase the molecular weight, then the state would be solid. So why is that? This is have to go back to Chem 122 that we learned from last term. So I'm gonna do review Chem 122. The topic that involved with this is called the intermolecular forces. The intermolecular forces that we learned from Chem 122 are, the first one is dispersion. The second one is dipole-dipole. The third one is hydrogen bonding. And the last one is ion dipole. The strength of the intermolecular forces will determine the physical state of the compound. Dispersion is the weakest type of IMF, and ion dipole would be the strongest type of IMF. Dispersion intermolecular forces appears in all molecules, whether the molecule is polar or nonpolar. The dipole-dipole will present in the polar molecules. The hydrogen bond will present in the polar molecule that contain hydrogen connected to nitrogen, or hydrogen connected to fluorine, or hydrogen that connected to oxygen. An ion dipole, the name implies that this type of interaction would be the interaction between the ions, whether it's going to be cation or anion, with the polar molecule that contain the dipole moment. And when you consider the alkanes molecules, you will see that of these alkane contain carbon and hydrogen. Each of these bonds are non-polar bond. Of these are non-polar bond. Therefore, the molecule of alkanes are considered to be a non-polar molecules. The type of IMF that present in the non-polar molecules would be only dispersion. And from what we learned from last term, the dispersion strength also determined by the molecular weight and also the structure of the compound as well. The molecule that contain higher molecular weight has more atoms within the molecule, have higher number of electron density. Therefore, the dispersion force would be stronger because it's going to be induced into the temporary dipole very easily. So in this case, we can conclude that as molecular weight increase, you are going to observe that the intermolecular force, which is a dispersion, also going to be stronger as well. It will increase. And another one is the structure. When you have a long chain structure like this, okay, compared to branch that look like this, okay, the long chain structure would be able to interact with each other with greater interaction. Therefore, the long chain molecular structure would have a stronger dispersion. Okay, and if you have branch would have weaker dispersion. Okay, according to this, then we can look at why some of them are in gas state and some of them are in solid or liquid, right? So, for example, right, so we know that these alkanes, right, are non-polar molecule. Therefore, only dispersion would present in this molecule. The next thing we're going to take a look at is which one would have the stronger dispersion then, because since it's only dispersion that present. Then next thing we're going to look at the molecular weight. As you see, right, as the molecular weight increase, as the molecule become heavier, you will see that it's going to end up having a stronger dispersion. As the strength of the dispersion increase, the molecule tied up together more strongly. Therefore, the physical state would change from gas that is more dispersed, right, to liquid that is more condensed, which is indicate that the molecule hold up by each other more strongly, and the strongest one would be in the solid state. And that also going to affect the melting point and boiling point as well. For example, if you have the molecule that have a weaker strength of the intermolecular forces, such as the dispersion, you will see that it doesn't require much energy to change the state from liquid to gas, right? So that therefore the boiling point would be low. However, if the molecule contain a stronger dispersion, the molecule hold within the molecule with by each other stronger. Therefore, in order to convert from liquid to gas, it's going to require more energy. Therefore, the boiling point would go up. And we can apply that concept in example 1 here. Okay, so this is similar to Chem 122 that you see before. So example 1, we are going to rank the following structure in boiling point, increasing in boiling point, right? We're gonna go from the lowest to the highest. We're gonna rank from 1 to 4. Okay, so pretty much in this case, what you will need to know is that we are going to consider the type of intermolecular forces that present in each of these compounds. Okay, so let's start with the first one. The first one, this molecule contains only carbon and hydrogen. How many? You can count, right? So we can go ahead, count the number of carbon and hydrogen. The number of carbon in this molecule, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is C10. And because it contains all single bond, therefore the number of hydrogen would equal to 2n plus 2. That is come out to be 22. Okay, if you are not sure, you can go ahead count the number of hydrogen, but this way is a lot faster. If you know the generic formula of an alkane, you can go ahead calculate by using that formula. Okay, so if you add all of these hydrogen together, you're also gonna get 22 as well. Okay, because this is an alkane, therefore the type of IMF that present in this structure would be dispersion. Okay, it's only going to be dispersion. Now let's take a look at the next molecule. The next molecule also contain only single bond as well. This is going to be an example of an alkane. Okay, so because it's an alkane, therefore the chemical formula would be the number of carbon, right? And then number of hydrogen would come from number of carbon times 2 plus 2, right? So let's take a look at how many carbon here. So number of carbon would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is C10, and therefore hydrogen would be 10 times 2 equal to 20, plus 2 would be 22 also. If you're looking at these two structures, when you compare them, these two structures contain the same chemical formula, but different structure, right? This one is the long chain, this one is branch. These two are considered to be structural isomer. Okay, so pretty much these two considered to be structural isomer. And again, because this compound is an alkane, therefore the type of IMF that present in this compound would be dispersion. We will take a look at the next molecule. The next molecule, these contain the alkane part, but we have an additional type of element, which is oxygen, that is appeared within the molecule. This group right here that attached to an alkane, we call this functional group. You are going to see more detail of the functional group in chapter 19.6. If you want to find out the chemical formula of this structure, then the alkane generic chemical formula would not apply to this structure because we have another type of element that appear to here. Therefore, in order to find out the chemical formula, you will need to count number of carbon, number of hydrogen, and also include the oxygen as well. So then the number of carbon for this equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's C9H. Okay, so hydrogen, there are 3 from this carbon right here, so 3 plus 2, right? Plus 2, plus 2, plus 2, plus 2, plus 2, and plus 3 here. And it's come out to equal to 18, and then include oxygen as well. This molecule contain the nonpolar part, but also is contain the polar part between the bond of oxygen and carbon as well. So the overall, this molecule right here would have a polar part. Therefore, this molecule would exhibit dipole-dipole as well. And since dipole-dipole is stronger than dispersion, therefore I'm just gonna list dipole-dipole. Okay, so again, pretty much this molecule would contain dispersion and dipole-dipole, but because dipole-dipole stronger than dispersion, therefore I'm going to list dipole-dipole because this molecule is a polar molecule. Okay, so the next one, we are going to do the same thing for the next. Go ahead, write out the chemical formula for this one, right? So chemical formula of this would equal to C1, 2, 3, 4, 5, 6, 7, 8, C8, H. That would be 3 here, 2, 2, 2, 2, 2, 2, 2, and then 1 here. Add them together, you will get 18, and then oxygen. This molecule would contain dispersion as the intermolecular forces, and also because of the OH group, right? So this would also is a polar molecule, so it's also going to contain dipole-dipole, but it's going to be a special polar molecule because the hydrogen connect directly to the oxygen. So the strongest type of IMF that present in this molecule would be the hydrogen bond, which is stronger than dispersion and dipole-dipole. If you don't want to count the number of carbon, hydrogen, or oxygen, the thing that you can do is that start looking at the structure, right? For example, this structure right here is contain a negative ion. Therefore, this structure considered to be an anion. And we have water molecule, H2O. Water molecule contained considered to be polar molecule. Okay, so this is what you have is polar molecule of water. This is polar. And this part right here is the anion, right, which is the negative ion. Therefore, the type of intermolecular forces that present, which is the strongest between the ion and the polar molecule, we would call this ion dipole. Okay, so this is an example of the ion dipole. Now, before we rank the boiling point, you first will need to know that the boiling point increase as the strength of the intermolecular forces increased, which means that if you want to know which one has the highest boiling point, you will need to find out which one have the strongest intermolecular forces. Okay, so in this case, you probably see that the number of carbon are relatively similar, right? So if you count this number of carbon is 1, 2, 3, 4, 5, 6, 7. So it's similar, even though this one have a lower molecular weight. But because it contained in the stronger type of IMF, therefore this molecule would have a stronger intermolecular forces because it's contained the ion dipole. Therefore, this one would have the strongest IMF, and also is going to have the highest boiling point. Therefore, the rank of this would be number 4, right, which is the highest boiling point. Next thing, you will see that the hydrogen bonds have the second strongest IMF type. Therefore, this would be the second highest boiling point. And the next one contain dipole-dipole, which is stronger than the dispersion. Therefore, this molecule would have the boiling point lower than the hydrogen bondings, but higher than those compounds that contain dispersion. Now, between these two that contain the same type of IMF, clearly this structure right here is the long chain. This one is the branch. The long chain would have a greater surface area of interaction than the branch. Therefore, the strength of the dispersion for the long chain would be stronger than the dispersion. Therefore, the boiling point of the first molecule right here would be higher than this molecule with the branch. And I'm sorry about the scale here. The scale is 1 to 4, but we have 5 molecules, so I'm going to label this as 0. So the rank would be going from 0, which is the branch, followed by this molecule, followed by this molecule, followed by this molecule, and the highest boiling point would be the last molecule that contains ion dipole intermolecular force. Now let's take a look at next example. Example 2 asks us to find the chemical formula of an alkane, okay, that have the molar mass of 72 grams per mole. Right, so we know that the generic chemical formula of an alkane is CnH2n plus 2. And we know that for this molecule, if you add off this mass together from carbon and hydrogen, it should give you the molar mass of 72. Which means that if you know mass of carbon, which is from the periodic table, which is 12.011, we are going to multiply this by the number of N that we don't know, right? Because we want to find out the chemical formula, so we don't know N, okay? If you multiply this, you are going to get the total mass of the carbon within the molecule. Add these together, okay? We are going to add this together with the mass that come from hydrogen, okay? And the mass that come from hydrogen is coming from the number of hydrogen that present in the molecule, which is 2n plus 2, okay? And we are going to multiply this number of hydrogen by the molar mass of hydrogen, which is 1.008 grams per mole according to the periodic table. Again, so 12.011 from the periodic table. This is also mass of hydrogen from the periodic table as well. These are the mass of one carbon, right? This one is one hydrogen. If we have n carbon, then you multiply to it. If you have 2n plus 2 hydrogen, then you multiply to it. So we are going to set these off. These add up together is going to give you the molar mass, which is the problem give us 72 grams per mole. And as you see, if you set up this equation, we have only one unknown variable, which is n. Therefore, if you can solve for n, you will know how many subscript, right, that should go into those. And eventually you will get the chemical formula of this alkane. Okay, so let's go ahead solve for this. First step, you need to multiply 12 by n. So you are going to get 12.011 n plus, this is when you need to distribute, right? So you are going to distribute 1.008 to 2n and distribute this number to 2 as well. If you do that, you are going to obtain 2.016 n, right? Because you multiply this number by the 2n and plus, okay, so the next one is multiply this number to 2. You are going to obtain 2.016, okay, which is equal to 72. What you do next is move this number to the other side, okay, combine this n together, and then whatever number that you get, divide by that, right? Divide both sides by that. You are going to get the n equal to 4.989, but n have to be the whole number because we want to know how many carbon. So round this up to the whole number, that would be 5. Therefore, plug this back into the generic chemical formula. You are going to get this chemical formula equal to C5H12. Okay, so this would be the chemical formula that contain the molar mass of 72 grams per mole. If you are not sure, you can go ahead, add all of these mass together. You should also get 72 also. Next, let's take a look at alkanes, another type of hydrocarbons that contain one or more double bonds. Let's take a look at alkane that contain 4 carbon, C4, and the name for this would be butene. Okay, so butene is ending with ene. Does indicate that this type of hydrocarbon belongs to an alkene. Before we count the number of hydrogen, I would like to just go ahead, draw these 4 carbon first. So 1, 2, 3, 4. Okay, and if this is an alkane, which is contain only single bond, you will see that of these would contain 1 hydrogen for each carbon, right? So that's what it would be. Okay, but because this is an alkene, therefore we'll need to make sure that we introduce the double bond into this molecule. Okay, so if I introduce double bond into this molecule, let's say I would like to add double bond between these 2 carbon right here. So if I add this double bond to these 2 carbon, you will need to see that these 2 carbon, if you add double bond directly without get rid of hydrogen, you will see that the carbon have exceed octet, right? Because there are 10 bonds total, 10 electrons. So this is not going to follow the octet. Therefore, whenever that we introduce the double bond, you will need to eliminate 2 hydrogen. Okay, so therefore in this case, we will need to eliminate these 2 hydrogen. So this would be a representation of the structure of butene. Okay. And again, because the double bond can be in this location or at this location, therefore butene will have different isomer as well, right? That's what we call structural isomer because the location of the double bond will be at different place. Now, if you count the number of hydrogen now, the number of hydrogen would be C4H8 because it's going from an alkane, right, C4H10, but because we eliminate 2 hydrogen, therefore the total hydrogen would be just 8, right? So 1, 2, 3, 4, 5, 6, 7, 8, for example. And if you introduce more double bond, for example, if you have C4 again, so if you introduce 1, 2, 3, 4, C4 again here, and we already introduced 1, right? And these have only this many hydrogen left. Now if I want to introduce 1 more, okay, you can see that if I want to introduce 1 more, either the double bond right here or right here, I will need to eliminate 2 more hydrogen. If I put it right here, I need to eliminate these 2 hydrogen. If I put it right here, it's need to eliminate these 2 hydrogen. Therefore, in this case, the more you add a double bond, the number of hydrogen will be decreased. Okay, so for example, let's say I'm going to introduce right here, right? So in this case, you can erase those 2 hydrogen. So I'm going to erase this hydrogen right here. Okay, so now this is also an example of alkene as well because it contains double bond. Okay, and the number of hydrogen would be 2 more less. So hydrogen would be, instead of H8, now it would be H6. Again, every double bond that you add to the structure, you will need to remove 2 more hydrogen. And alkene are the unsaturated hydrocarbon, which means that you can add more hydrogen into the molecule, right? Because it contains the double bond can be open and receive 2 more hydrogen, as we did earlier. By, in order to make double bond, you get rid of hydrogen, but in order to add hydrogen, you just need to open those double bond, right? So, or break the double bond into the single bond. You might be familiar with unsaturated fat, which come directly from the fact that those fat contain this double bond within the molecule that can be hydrogenated, which means that can be add hydrogen into the molecules. Next hydrocarbon is alkyl. Alkyl contain 1 or more triple bond. The name of an alkyl would ending with I. For example, if you have C4, right, the name of this would be butyl. Okay, so let's take a look at how many hydrogen here. The structure of butyl would be 4 carbon connected to each other. Next, I'm going to start adding all the hydrogen in here. We are going to introduce triple bond later, but I would like you to understand how many hydrogen that we need to remove, right, if we introduce triple bond. Okay, so again, this is a structure of an alkane that we learned earlier. The generic chemical formula of this would be CnH2n plus 2, right? So if you count this together, it would be C4H10. But we are going to introduce triple bond to the structure because we want to make this to be an alkyl. If I introduce triple bond, which means that you are going to draw 2 more lines right here. So 1, 2, you will see that if you do that, these 2 carbon will have exceed octet. So it's not going to be valid Lewis structure. Therefore, we will need to eliminate hydrogen. Every time that you introduce this bond right here, you eliminate 2, right? Therefore, if you introduce a triple bond, right, so 1, 2 here, you will need to eliminate total of 4 hydrogen. So therefore, in this case, I need to eliminate these 2 hydrogen to make the carbon to have an octet, right? So therefore, in this case, because you eliminate 4 hydrogen, the chemical formula would be C4H6, okay, because you eliminate 4. So the conclusion is that if you add double bond, you need to get rid of 2 hydrogen, right? If you add triple bond, then you need to get rid of 4 hydrogen, for example. The alkynes also considered to be unsaturated hydrocarbon as well because we can add the hydrogen into the molecule by do the hydrogenation process that adding hydrogen into the triple bond. And as you see, the type of alkene and alkyl is connected by the nonpolar bonds. Therefore, these 2 molecules are going to be nonpolar molecules that has the dispersion present in the molecule as the IMF. Therefore, the trend for the boiling point and physical state would follow the alkane that we discussed previously. The hydrocarbon can also contain the group that call aromatic hydrocarbon as well. The aromatic hydrocarbon would contain this structure of the benzene ring, or what we call aromatic ring. The name aroma comes from the fact that several of these compounds that contain this type of benzene ring has the aroma smell, right? For example, almond or vanilla or cinnamon or clove, right? So those contain aromatic ring that produce the smell that specifically for these molecules. I'm not going to go over much of the detail for aromatic hydrocarbon, but what I expect you to know from here is that you need to be able to recognize the aromatic ring or the benzene ring. The three types of hydrocarbon that we will focus the most would be an alkane, alkene, and alkynes. And here I have chemistry joke for you. I hope this make your day. Right, so for example, airplane, right, ending with "an," it would have single wing. And for airplane, right, that ending with "in," it would be an contain double wing. And alply ending with "I" would have triple wing. So similar to alkane, alkene, and alkyne. Now let's take a look at example 3. Example 3, identify each of the following as alkane, alkene, or alkyne, and assume that the hydrocarbons are not cyclic, and we are going to talk about this later, and there is not more than one multiple bond. Okay, so that means we are going to look at just one multiple bond. Okay, so for example, if there is double bond, it's just going to be one. If it's triple bond, it's just going to be one, okay, in this molecule. This problem again rely on the fact that you will need to know the generic chemical formula of an alkane. An alkane generic chemical formula is CnH2n plus 2. Anything that doesn't have this chemical formula, it will not be classified as an alkane. Okay, every time that you introduce one double bond, you are going to get rid of 2 hydrogen, so it would be 2 less hydrogen in the structure. And every time when the triple bond is introduced, then we will need to get rid of 4 hydrogen from this generic structure, right? So let's go ahead start with A. Okay, so A. So I'm going to start with A. We have 5 carbon. So 5 carbon, so does it match with CnH2n plus 2? So 5, the number of hydrogen would equal to 5 times 2 plus 2, that would be 12. And yes, this chemical formula matching with the alkane formula, so therefore A would be an example of alkane. Okay, because the chemical formula matching that generic chemical formula of an alkane. Now let's take a look at B. Okay, so B, if I write the generic chemical formula of C3H would be C3 times 2 would be 6, 6 plus 2 would be 8. However, this is not matching what is given. It's given only 6. Therefore, we see that it's missing 2 hydrogen, right? So it's missing 2 hydrogen here. Missing 2 hydrogen means that we are eliminating 2 hydrogen out of this structure, right, to make it to be this structure. Therefore, it's implied that we are introducing a double bond into the structure. Therefore, this would be an example of an alkene. Okay, that's for example. Now let's take a look at C. C, same thing. We are going to write out a generic chemical formula of C4. So it would be C4H. 4 times 2 would be 8. 8 plus 2 would be 10. So this would be of the alkane, right? But the given structure, the given formula is not the same as the alkane. Therefore, this is not an alkane. Okay, so how many hydrogen are different? That's what we're going to take a look at next, right? So these two different by 4 hydrogen. Okay, so it's missing 4 hydrogen. Therefore, we are going to introduce only one type of bond, one type of multiple bond, right? So that means in this case, it can't be 2 double bond. It have to be 1 triple bond instead. Therefore, this would be an example of alkyne. Okay, so that's an example 3. And you will see similar problem again in homework number 10. Now let's take a look at example 4. Example 4 asks us to determine the chemical formula and also draw the condensed structural formula as well. Okay, so let's take a look at the first structure. The easiest one to do this, instead of counting the number of hydrogen and hydrogen within the molecule, is take longer to make this faster. What you need to do is that you will need to recognize that this is an alkane because it has no double bond or triple bond and it doesn't contain any other element. Therefore, we are going to count the number of carbon okay, because the number of carbon will help us determine number of hydrogen. Okay, so this is an alkane that contain 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon. Okay, therefore the number of hydrogen would be 10 times 2 plus 2 equal to 22. Okay, if you are not sure, you can go ahead count those and you are going to end up with 22 hydrogen also. Okay, we can do this of this. Okay, so let's go ahead do the next. The next one, again, of this molecule that doesn't contain any other element, therefore our chemical formula would be just CH. That means we will need to recognize which type of alkane, which type of alkene, or which type of alkyne. Okay, so let's take a look at the next one, which is the second molecule here. How many carbon is 1, 2, 3, 4, 5, 6? So it would be 6 carbon. If this molecule were an alkane, the chemical formula would be C6H14, right? Because 6 times 2, 12, plus 2 is 14. However, this molecule is not an alkane. Therefore, it's not going to be 14. Okay, so the number of hydrogen would be different. This molecule is contain one double bond, and we just see previously every time that you introduce double bond, you will need to get rid of 2 hydrogen away from the alkane. Therefore, the correct number of hydrogen would be only 12. Okay, so it would be C6H12 because we get rid of 2 hydrogen from the alkane structure because we introduce one double bond. Do the same thing, right? So the third structure contain 1, 2, 3, 4, 5, 6 carbon. Again, I'm going to start this with the alkane chemical formula, which is 14. Again, 14 come from the generic chemical formula of an alkane. But again, this is not an alkane. We introduced 2 double bond. Each double bond would require 2 hydrogen that we need to remove. Since we introduced 2 double bond, therefore we need to remove 4 hydrogen. Therefore, in this case, this number of hydrogen would not equal to 14, but it's going to equal to 10. Okay, so you are welcome to count the number of hydrogen as well if you're not sure. Okay, so let's take a look at next. Next, this one contain 1, 2, 3, 4, 5 carbon. 5 times 2 is 10 plus 2 is 12, right? And because this is a structure of alkane, so we can just leave it as that. Okay, so the next one is the ring. Okay, so let's take a look at the ring structure. So the ring structure, we have how many carbon here? So 1, 2, 3, 4, 5. We have 5 carbon. And this seems to be an alkane too because it doesn't contain any double bond. Okay, so I'm just going to go ahead, write this as the structure of alkane, which is C5H12. But let's actually make sure, let's take a look at that, right? So how many hydrogen here exactly? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, wait a second. If we count number of hydrogen is 10, but our formula is only have 12. Why it's not the same, right? Which is if you count this, right, it's gonna match with that, right? For example, if you count this one, hydrogen would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which is identical to what we just talked about, right? If you count this again, you are going to get 22 as well. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, which is also matched with what we discussed previously. But how come these structures are not matched, right? So it's not the same. So why is that? Okay, so let's take a look at this. So if you have 5 carbon in an alkane structure, okay, so I'm going to go ahead, draw this. So it would be 1, 2, 3, 4, 5. So that way it's easier for us to form the ring. Okay, so I'm going to go ahead, draw number of hydrogen. So it would be 3 on the last one, would be 2 right here, 2 right here. and 2 right here, and it would be 3, right? Which is this structure is going to be the conformational isomer of this one, okay, because it contains 5 carbon and 12 hydrogen. Now, this is called the chain structure, right, because it's going to be a long chain. Now, if you do a cyclic, which is the ring form, okay, so I'm going to introduce the bond between, let me draw this better. So let me draw this separately. So hydrogen would be right here. Okay, so now think about this. If I'm going to make a 5-membered ring, I need to connect between these 2 carbon, right? So if I do it, okay, so if I am adding bond between these 2 carbon, you will see that these 2 carbon would exceed an octet, right? So because these 2 carbon would have 5 bonds for carbon, which contain 10 electron total around it. Therefore, this structure is invalid. To make this valid, whenever that you introduce the ring or when you make the ring formation, you will also need to get rid of 2 hydrogen, right? So 1, 2, in order to make the carbon to have an octet. Therefore, in this case, instead of having C5H12, we will need to get rid of 2 hydrogen. Therefore, the correct chemical formula would be C5H10. Okay, so this would be C5H10. Okay, so again, if you count the number of hydrogen, you will see that there will be 10 hydrogen similar to this, right? So that means in this case, every time you introduce the ring, you need to get rid of 2 hydrogen. Okay, so because of that. Okay, so I'm going to go ahead erase these structures, that way it's clearer. We have more room to work on the next step. Okay, so note, I'm gonna make note as well. So every time when ring introduced, you need to remove 2 hydrogen also. Okay, so similar to when you add a bond, you remove 2 hydrogen. Now let's take a look at the last structure. Last structure contains rings and also double bond and also triple bond. So let's start this with the chemical formula of a regular alkane. Okay, so it's gonna be how many carbon here? So note that the triple bond, in order to make triple bond, you will need 2 carbon between each other, right? Between the that have the triple bond between them. Okay, so 1 carbon, 2 carbon, 3, 4, 5, 6, 7, 8, 9. So we have 9 carbon. Okay, so it would be C9 in this case. Okay, so let's write C9. How many hydrogen then? Let's treat this as an alkane before we can remove all of those hydrogen. So if this were an alkane, it's going to be C9H. 9 times 2 is 18. 18 plus 2 is 20. It would be C9H20. But this is not going to be C9H20 because we have double bond, we have triple bond, we have ring structure, and we know that every time when a double bond introduced, we need to remove 2 hydrogen. Every time when triple bond introduced, we need to remove 4 hydrogen. And when the ring is introduced, we need to remove 2 hydrogen. Therefore, the number of hydrogen should equal to 20 minus 8, which is going to equal to 12. Therefore, the correct chemical formula of this structure would be C9H12. Okay, so I'm going to highlight this so that way we know. And if you're not sure, let's go ahead count the number of hydrogen to see whether we make the analysis correctly or not. So this carbon right here would contain 1 more hydrogen. Okay, so 1, this would contain 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, so it's matching what we predicted. Right, this would be the answer for the first part of this example, right? Because it asks us to write out the chemical formula. The next part is to draw the condensed structure, okay, of this. Let's take a look at the first one. Okay, so I'm gonna start on this side. So CH3, okay, followed by CH2, followed by CH, and this CH attached to another carbon and also attached to another group CH3. So this group CH3 is separated from other carbon. So we are going to use parentheses to describe this CH3. So it would be parentheses CH3. And then followed by the next carbon that connected to this carbon, it would be C. But this carbon contain two group of CH3. So therefore you can use parentheses CH3. And then outside parentheses would be subscript 2. Right? Followed by the next one would be CH, right? Because this carbon connected to hydrogen, and this carbon right here connected to CH3. Therefore, we can use the parentheses CH3 and then subscript 2 for that. The next one is we'll start with CH3, CH, double bond C, okay, and then parentheses CH3 that connected to CH2, and then CH3. Note that sometimes you don't need to specify double bond as well. You can just condense all this together and ignore that, right? Because the lacking of number of hydrogen, it will imply that we will need to add double bond into the structure anyways. What do I mean by that? Let's take a look at the next example. Okay, so the next example, we're going to start with CH3, okay, CH, C, parentheses, CH3, followed by CH, followed by CH2. Again, when you go from this condensed structure to the line angle structure, you will see that when you draw it out, the carbon right here would lack of octet. That's when you will need to add a double bond, right? So this carbon right here would lack an octet. That's when you need to add the double bond. Therefore, you don't need to actually specify the double bond as well. But writing out double bond, it just becomes clearer. Okay, so let's take a look at the next one. The next one, it would be CH3, CH2, 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 CH3, right? So we can condense this same CH2 together. It would be CH3, parentheses, CH2, and there are 3 of them. So outside parentheses, it would be subscript 3, and then followed by CH3. And the condensed structure for the ring, you need to actually provide the line connection between those, right? So it's just going to be CH2, 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 CH2 that connected to that, right? So that would be the condensed structure. And same thing for the last one. The condensed structure of this would also be the structure of the 6-membered ring. So CH2, okay, CH, So that would be just one carbon. And followed by CH2, 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 and that. And then here you can draw CH2, right? CCH, you can do that as well.